Welcome back everyone to CMPT 726 Machine Learning. So last time we wrapped up the neural network architectures and therefore finished talking about neural networks. And then we started to talk about the general problem of classification. We then delved deeply into a classical technique called support vector machines. And we first covered the goal of support vector machines, which is to determine a decision boundary that separates data from two different classes. And we began with some geometric interpretation, kind of relating the geometry and the math behind SVM. We also covered some terminology. So I think the most important ones are margin, decision boundary, and support vectors. So especially this decision boundary. So this term is quite general. It doesn't just apply to SVM. So anytime you have a classification algorithm or classification method, usually we want to find decision boundaries that separate different classes. We then talked about the mathematical formulation of SVM, and we did many steps of simplification to obtain a relatively simple constrained optimization problem. The solution of the optimization problem represents the decision boundary that should separate the two different classes. And then we began talking about the solution to this constrained optimization problem. And we began that discussion by talking about weak duality. So let's continue from there. So in weak duality, we talked about it from the perspective of a general constrained optimization problem. So min over theta of f of theta, the objective function, which are subject to inequality and equality constraints. There was some more terminology here, the feasible region and also feasible solutions, which are from the feasible region. Okay, so we want to find a theta in the feasible region that is that actually minimizes the function f. So to do that, we talked about the generalized Lagrangian, which is basically this L function, which is equal to the objective plus what looks like some penalty terms, where we get penalized for violating the constraints, i.e. when GIs are positive. And then we also get penalized when the h functions are not zeros, right? So that's basically getting penalized for constraint violation. And we set up a function to formalize this penalty. This function is called phi of theta. And the function maximizes over lambda with positive lambda components, as well as nu, where the new components of nu are unrestricted. And by defining the function phi this way, we actually get that optimizing f subject to these constraints is actually equivalent to optimizing phi. And we went over the math last time, but the intuitive reason is that whenever we have constraint violation, the penalty coefficients lambda I and nu I can be set so large that the value of L goes to infinity, and therefore phi goes to infinity. Okay, so basically minimizing over theta of phi of theta is actually the same thing as minimizing over theta for f subject to the constraints. But now with the phi function, it's a bit more convenient. We don't have to explicitly write down the constraints. So the complexity is hidden in this writing down phi in two cases, right? And of course, phi has a maximum inside. Okay, so then that allowed us to write down the solution, P star, to the original constrained optimization problem. So we call this the primal problem. The primal problem, when we expand it out, has a min-max. And when we switch the min-max into a max-min, then we get the dual problem. And the objective value of the dual problem was denoted D star. So we did a few steps of math to show the relationship between P star and D star. So we began with some pretty simple facts to kind of follow these facts, the most important thing was for us to realize that when we start with a function of many variables and we minimize over some of the variables, the result is actually a function of the remaining variables that we did not optimize over. So the first fact we used was for any theta prime, which is the first argument of L of theta prime, lambda, and nu is always greater than or equal to minimizing over theta for the same function, right? So this is kind of the meaning of min. And this is true no matter what you choose for the other variables, right? So regardless of any value that lambda and nu can take on. Next, we considered a point, lambda 0 and nu 0, which maximizes this function, so this function is actually a function of two variables now, lambda and nu, but let's consider a point that maximizes this function. Okay, from 1, we know that 1 is true for any lambda and nu. In particular, it is true for lambda 0, nu 0. That's just some particular value of lambda and nu. Okay, but then, again, the 1 still holds, right? So this is greater than or equal to min over theta of L. Okay, but now if we plug in lambda 0 and nu 0, this is the same thing as max over lambda and nu, min over theta of L. And this is just because that we have defined lambda and nu to be the values of lambda 0 and nu 0. Those are the values of lambda and nu that maximizes this function. So this is exactly what we're writing here, right? This is the function, this whole part, including the min, is a function of lambda and nu, and then we're maximizing over lambda and nu. Okay. So continuing on, next, we said that for every theta prime, so max over lambda and nu of L of theta prime, lambda and nu is always greater than L of theta prime and lambda 0, nu 0. So why is this? Well, that's because so for all theta prime means that we can plug in any theta prime, right? So no matter what theta prime we plug in here, if we maximize over lambda and nu afterwards, that's going to be always greater than or equal to simply plugging in a particular value of lambda 0 and nu 0. So that's why this inequality holds. So now putting everything together, we get this long inequality, which started off with this one. So this part is the first inequality here. And then we continue finishing the long inequality by looking at equation 2 over here. So this term looks like that one, this term, and then everything else follows. Right, so we did this a bit more slowly last time, but just to recap a little bit on the slides for a second time. Okay, so now we're just going to take the first term, greater than or equal to the last term, and then copy it over to this slide. So we note that for any theta prime, this is true. So that was from the last slide. So now consider a particular theta prime, one that minimizes this function. So remember that this function before the max was a function of three variables, L of theta prime, lambda, nu. After we maximize over lambda and nu, this whole thing is now just a function of one variable. So we're actually one vector, right? So it's just a function of theta prime. So consider the theta prime that minimizes this function. For this particular theta prime, equation 4 is still going to be true, right? So basically we can put this theta 0 prime in here, and equation 4 will still be true. But then this is going to be the same as min over theta of this function. So this is actually the same as this, right? This is basically plugging in the minimizing theta prime. But this is actually writing down, okay, what is the value of this function when we minimize over theta? Okay. So So then we still keep the inequality. Now if you look at this again, the left-hand side is actually P star and the right-hand side is D star. Right, so that's what we had over here. So now we have shown that P star is always going to be greater than or equal to D star. So for now, it's just a bunch of mathematical facts for general optimization problems. We're now going to start to relate this general theory into what we're going to do for SVM. Right. So in general, the difference between P star and D star is called the duality gap. And sometimes, under some conditions, which we'll be talking about a bit later, the duality gap is 0, meaning that P star equals D star. In this case, we say that strong duality holds. So when strong duality holds, solving the primal problem is actually equivalent to solving the dual problem. So sometimes this is very helpful because maybe the primal problem, which is the original problem that we want to solve, could be very difficult to solve, or maybe it could be very computationally expensive to solve. Whereas solving the dual problem, which is equivalent to solving the primal problem, could be much easier. Right? So from a computational perspective, it might be helpful to solve the dual problem. Of course, this is only useful when, well, ideally we want strong duality to hold, right? Then there will actually literally be no difference between solving these two problems. Mathematically speaking, sometimes solving the dual problem can reveal some relationships between the optimal solution and the quantities given in the problem that maybe we could not see from the primal problem. So sometimes by solving the dual problem, in other words, we can interpret the solution better. So now specializing to SVMs. For SVM, it turns out that when we look at the dual problem, we will get computational efficiency benefits, and we will actually get some mathematical insights to the solution as well. It also allows us a way to generalize the SVM. So we'll talk about all of this later. Okay, so now let's apply, so now let's construct the primal and dual problems for the SVM using the using the generalized Lagrangian function. So first we're going to write down the primal form of the SVM. So remember SVM, the SVM problem was min over W and B of 1/2 2 norm of W squared, such that, so just going to use the shorthand for such that yi times W transpose xi minus B is greater than or equal to 1 for all I. Okay, so W and B together represent our decision boundary, and the xi and yi are our data points, where xi is basically the input vector, and then the yi is the label. The label can be plus or minus 1. Okay, so that's the SVM. So general, on the right hand side, let's write down the general optimization problem. The general optimization problem looks like min over theta of f of theta subject to gi of theta, right? Everything is a vector in general, less than or equal to 0, and hi, so for, let's just say for all I, and then hi of theta must be equal to 0 for all I. And so the primal problem, for the general optimization problem was max over lambda nu, where lambda I are all greater than or equal to 0 for all I, of min over theta of the generalized Lagrangian, which is theta, lambda, a function of theta, lambda, and nu. Okay, so that's the problem we need to solve. And then we should write down the generalized Lagrangian. So remember, the generalized Lagrangian looks like, it kind of looks like the original objective, except that we add penalty terms to it. So this is the original objective, f of theta, plus, so let's say we have k constraints, k inequality constraints, and L equality constraints. So now this is from I equals to 1 to k, lambda I g of theta, gi of theta, plus sum from I equals to 1 to L of nu, no vector on the nu here, I'm going to write nu I, hi of theta. Okay, let me move a little bit. Okay, so now we're going to apply the same thing to the SVM. So for SVM, let's see where I can write this, right? So for SVM, we have theta, which is equal to all of our parameters. So that's going to be W and B. And then, so now let's construct the generalized Lagrangian. So that means that for SVM, we have the generalized Lagrangian will be a function of theta, which is W and B, and also lambda and nu. And it's going to equal to our objective plus sum over I. So let's just say we have n data points, just like we had before, right? Capital N data points. So sum of I equals to 1 to n of lambda I, and then the constraint, right? So, well, what is the constraint? We have to put the constraint in the form of something less than or equal to 0. So, well, that's not too difficult, I guess. This is the same as 1 minus yi W transpose xi minus b less than or equal to 0. Okay, so then we put that in here. So 1 minus yi W transpose x minus b. Okay, so this is our inequality constraints. We don't, in the SVM, we do not have any equality constraint. So this is our L. So now we can write down the primal problem. So the primal problem, sorry, this is actually the dual problem over here. I think I said something wrong just now. This is a dual problem, not primal. Okay, because we already flipped the max and min in here. So this is a dual problem. So for the SVM, the dual problem is going to be the same, but it's a little simpler. So it's going to be max over lambda, where all the components are greater than or equal to 0 for all I, and then min over W and B of our Lagrangian, generalized Lagrangian, which is given below. Okay. So we can kind of see that we have a max-min problem, and then the objective here for the dual problem is this generalized Lagrangian over here. So what we're going to do next is actually to try to solve this optimization problem by hand. Okay, so it looks a little difficult, but it turns out that it is possible to do. So what we're going to do is we're going to simplify L a little bit. We're going to focus on we're going to simplify L and then focus on the inner optimization problem. So we're just going to write down what min over W and B of L is, right? So we're going to perform this minimization to turn this L function into a function of only lambda and nu. So that's the first step. And we're going to do this by taking the gradient of L, setting it to 0, and then confirming that this is indeed the minimum by showing that L is convex. Okay, so we're going to do all of that now. So let's do a bit of simplification. This is, since we're going to be taking gradients, it's easy. It's better to write out everything in terms of inner products. And then let's also expand. Let's expand the summation. So it's lambda I times 1 minus lambda I yi W transpose X minus B. Okay, I guess we can expand this out further as well. Right, so lambda yi W transpose X minus lambda I yi. So lambda I yi B. So it should be a plus because we have a minus and minus. Okay. So let's separate this general problem. Okay. So now let's take the gradient of this expression. So normally when you take the gradient, what exactly is the gradient? Well, the gradient is basically all the partial derivatives of the function. In this case, we're going to be focusing on the variables W and B. So we would like to take all the partial derivatives of L with respect to every component of W and B. We're going to do W first. So partial L, partial W. So this is a gradient because W is a vector. So this is actually equal to, well, now we have a quadratic form. And the gradient of the quadratic form, well, let's do an aside here, right? So remember that if we had a quadratic form, X transpose AX, and we take the gradient, I guess in this case it would be the Jacobian. This is actually equal to A plus A transpose times X. Okay, and then the other thing we need here is that when we take the gradient of a linear expression, so A transpose X, with respect to X, then that just equals to the vector A. Okay, so I think this is what we need. Okay, so the first one, this is the quadratic form, 1/2 W transpose identity W. So there's really a hidden identity in here. So we can use this, we can kind of use the property that we just wrote down for the matrix derivative. So this is going to be 1/2 identity plus identity transpose times W plus, we're going to differentiate the sum term by term. Okay, so lambda does not depend on W, so we don't need to worry about that, right? And then the last term, lambda I yi B, those don't depend on W as well. So the only thing we have is the middle term. Let's put a minus in front here. In the middle term, we have lambda I yi x xi. Sorry, I forgot to have an xi over here. Okay, and that's because this part is just going to be xi transpose W, right? So when we take the gradient with, this is equal. When we take the gradient with respect to W, then we just get xi. Okay. So now we're going to set this to 0 and then also simplify the right side. We know that identity and identity transpose is going to be the same. So this is really 2 identity, and then the 2's cancel, and then the identity times W will just be W minus the summation of over, from I equals to 1 to n of lambda I yi xi, the whole thing must be 0. So then we have w must be equal to this summation. Okay. So then this is basically the w at the critical point. Okay, so now we also need to take the partial derivative of L with respect to B. If you look at the expression for L, the first term does not depend on B. The only term that depends on B is going to be the last term inside the summation. So that's going to be summation from I equals to 1 to n. And then the partial derivative will just be lambda I yi. And then that should be 0, of course, because we're setting the gradient to 0. So let's call this equation 1, equation 2. And what we have here is that at critical points, or I should say critical points satisfy one and 2. Okay, so far so good. So this is basically taking the gradient, setting to 0, and then see what the critical point, what conditions do the critical points need to satisfy. But that's not good enough, because we still need to verify that the function is actually a convex function. If we cannot verify that the function is convex, then the critical point may not be a minimum, right? So we need to show that L is convex. So to show L is convex, we need to we need to take the Hessian of L. So the Hessian of L is going to be given by partial squared L partial WB partial WB transpose. And then this is kind of like a block, writing down the Hessian in blocks. So this is actually going to be equal to partial squared L partial W transpose, partial squared L partial W. Actually, I think the order should be partial B first, partial W transpose, and then we have partial squared L partial W transpose partial B, and finally partial squared L partial B partial B. Okay, so now we have to compute these 4 elements. So this is actually equal to, it turns out that this will be, we can actually do this in one line. So if you look at partial squared L partial W, well, what that means is that we have to look at what partial L partial W is, and that is actually here. And we just want to take the Jacobian of this partial L partial W with respect to W again. The only term that depends on W is the first term, and it's actually just W. So then the left top part of the matrix is just identity. Next, we're going to be looking at partial squared L partial B partial W. So then we have to look at actually, if you look at partial L partial B, you realize that it doesn't depend on W, right? So this does not depend on W. It's a little ugly writing. Let me fix this. It should be lambda over here. And if you look at partial L partial W over here, this part doesn't depend on B, right? So actually it turns out that both of these are just going to be 0, because when you take the partial derivative with B, with respect to B, the expression no longer depends on w, right? And vice versa. So when you do the partial derivatives in both ways, you just get 0. And lastly, partial R partial B also doesn't depend on B. So then that's going to be a 0. Okay, and it turns out that this matrix is already diagonal with a lot of 1s for the identity part, and then there's going to be a single 0 at the end. Because it's already a diagonal matrix, we can read off the eigenvalues on the diagonal. And none of the eigenvalues are less than 0. So this matrix is actually positive semi-definite. So therefore, critical points, so before the conclusion was therefore critical points must satisfy 1 and 2. Now with the Hessian being positive semi-definite everywhere, this means that critical points must be global minimum. Right? Because with a positive semi-definite Hessian, the objective function is therefore going to be convex. And for convex functions, any critical points must be global minimum. Okay, so now backing up a little bit, what we're doing here with taking the gradient of L with respect to W and B and then setting it to 0, what we were trying to do was to find the min, to kind of solve the inner minimization problem over here. So now in order to so remember that when we minimize over W and B, actually we do not include the for all I inside here, right? So this is min over W and B. What we're solving is really this part. When we minimize over W and B, the result is going to be a function of only lambda and nu. So what we're going to do next is we're going to plug in our expression for W and B. Actually, we don't have an explicit expression for B, but we have something that must be satisfied. So these two, the equations 1 and 2, and we're going to plug that into the function L. After we plug everything into function L, then we no longer need to write the min, because basically we already solved the min part, right? So then it will be just the max over whatever we get after we plug things in. So let's do that. So min over, sorry about that, min over W and B of L of W B lambda nu, that is equal to, so we're gonna basically plug everything in here, right? So everywhere we see W, we're going to plug in equation 1. So that's going to be sum from 1 to n of lambda I yi xi transpose, and then times the same thing. Okay, and then plus lambda I equals 1 to n of lambda I minus lambda I yi, and then here we have a W, which is going to be sum from 1 equals to n of lambda I yi xi. Okay, transpose x. And finally, plus lambda I yi b. Okay, so this is just simply close bracket here, simply plugging some things in. Okay, so now we're going to start to simplify, and I'm going to try to avoid writing down too many of the repeated things because many of the steps are going to be pretty simple. So take a look at this term, including the transpose, right? This term is basically summing over some constants multiplied by a vector. So basically the only thing that we have to apply the transpose to is going to be the vector xi. So let's move that in here. And then similarly, we're going to move this other transpose over here to go with the xi only. Okay, so next we're going to, so now I guess I'll write a new line. I'm going to combine the two summations. So it's going to be I equals to n, and then the second summation we have to use a different index, j equals to 1 to n. And then we can, when we combine the summations, remember the order of summation doesn't matter when we have a finite number of terms. So the only thing we have to be careful is to make sure that we use different indices, because previously when we had the sums separately and then multiplied them together, it doesn't matter what the index of summation was, right? But when we combine them into two sums, they need to have different summations. Okay, so now order doesn't matter. So we have lambda I, lambda j. Let's write the lambdas first. Yi, yj, xi transpose xj. So that takes care of the first summation. And then let's write ditto for the second summation. So nothing changes there. Okay, so next we're going to write the same thing. Nothing changes for the first term, and we're going to work more on the second term. Actually, why don't we just do that up here to save space? So we're just going to split up all the summations. For example, we just have summation of lambda I minus summation of lambda I, yi, and then this, what used to be w here, summation over from 1 to n of lambda I, yi, xi transpose. Okay, and then we've got to be careful. Now the summation is nested. So actually I should have done that here already, because we have a nested summation. We have to use a different index. So all of these indices should be j. Okay. And then xi plus summation of lambda I, yi, b. Okay, let's continue. So all of that is actually equal to, let's not change the beginning. So nothing changes here, plus nothing changes here, still the summation over lambda I. And here we're just going to collect the summations, the double sum together. And we will now have something very similar to the first term, which is lambda I, lambda j, yi, yj, xi transpose xj. Okay, and then adding the last part. I guess it's probably worth writing down the first term now. Okay, 1/2 sum over I, sum over j, lambda I, lambda j, yi, yj, xi transpose xj. Okay, so if you look at this, we have 1/2 of something minus 1 of the same thing. So in the end, that just gives us minus 1/2 of that thing remaining. So then this whole thing, the first term is gone. We just have sum over lambda I, so that's from over here, minus 1/2 of this double sum that we had. Lambda I, lambda j, yi, yj, xi transpose xj. Okay, and then finally plus b, so b doesn't have an index, times summation of lambda I, yi. And this last part, we're going to be using equation 2. We know that lambda I, yi summing over all of that gives you 0. So this whole thing becomes 0. So in the end, so actually that's all we can simplify. So in the end, we have that the solution to this minimization is going to be sum over lambda I minus 1/2 times this double sum, lambda I, lambda j, yi, yj, xi transpose xj. Okay, so this is going to be the solution, which is a function of lambda and nu, right? Actually, we don't need to write the nu because we don't have any equality constraints in the original primal problem. So let me go back and fix this. There's no nu over here. Okay, no nu. Okay, so after we minimize over w and b, the result is this expression here, but it's still subject to the condition condition 2. We have fully plugged in condition 1, but condition 2 is still going to be here. So condition 2 is sum of lambda I, yi must be 0, right? So we're not really free to pick any lambda I and lambda j in these in these summations. We have to pick the lambda such that lambda I, yi is equal to 0. Okay, so now we can go all the way back to the dual problem and write it down. The dual problem is going to be max over lambda of the thing that we just solved, min over w and b of L, right? So finally, we have the dual problem, simplified. So it's going to be max over lambda, where all the lambda i's are greater than or equal to 0 for all I, of this summation that we just derived. Okay, it's just going to write that down one more time. So sum over I, sum over j of lambda I, lambda j, yi, yj, xi transpose xj. Okay, and then of course we are still subject to that additional constraint that we got from setting partial L partial b to 0. So subject to summation over I of lambda I, yi equals to 0. Okay, and then we can even write down lambda I greater than or equal to 0 for all I. That way we no longer have to write it up here. So now this looks more like a standard optimization problem. Okay, so basically what we have in the end, what we have is that we have the dual problem of SVM, and we also had the primal problem of SVM over here. In general, solving the primal problem may not be equivalent to solving the dual problem. In general, the primal, the objective value, the optimal objective value of the primal problem is in general going to be greater than or equal to the optimal objective value of the dual problem. In SVM, if they're equal, so suppose we can show that they're equal, then solving this problem, the primal problem will become equivalent to solving the dual problem. Okay, so maybe you can kind of predict that perhaps since I'm talking about it so much, maybe the SVM problem indeed satisfies strong duality. So we will definitely talk about that, but for now let's review a little bit. So basically what we have done in the written notes is to derive the dual problem for SVM. The primal problem looks like this. Min over w and b of 1/2 w2 norm squared subject to yi times w transpose xi minus b greater than or equal to 1 for all I. Right, so now following the construction of the generalized Lagrangian, we're going to do that for the SVM problem. So we have the objective written here, plus a summation which penalizes any constraint violation. So to do that, we multiply the constraints, the inequality constraints, with lambda I. So it's going to be lambda I times this part, which is obtained by rearranging this constraint so that the entire thing is something less than or equal to 0, which is kind of needed in a general form of inequality constraints. So now the dual problem becomes max over lambda, min over WB of this generalized Lagrangian. And then that's actually here. Okay, so what we're going to do next, or what we already did in the written notes, is basically to solve the inner optimization problem so that the result is no longer a function of W and B. We did that by looking at the generalized Lagrangian and then taking the gradient with respect to W and B and setting them to 0. We began by expanding L a little bit. And then taking the gradient of L with respect to W. So we have a quadratic term which gives us 1/2 I plus I transpose W. And then most of these terms don't depend on W except for this middle one. So then we had minus summation over I of lambda I, yi, xi. After simplifying a little bit, basically the 2 here cancels with the 1/2 and you only get W. Moving the summation to the other side, we just get W equals summation over I of lambda I, yi, xi. So that was the gradient with respect to W set to 0. For the gradient with respect to B, the only term that has a B is the last term. So that's pretty easy. We simply have 0 equals summation of lambda I, yi, which is the coefficient of B here. Both of these equations must hold at any critical point of L. So now to check that the critical points which satisfy these two conditions are indeed global minimum, we just want to show that L is actually a convex function. And we do that by taking all of the second gradients of L. And that's basically the Hessian. So then because we have broken down the parameter theta into 2 blocks, W and B, the Hessian can be written in a 2x2 block. The first block is basically taking the gradient of L with respect to W twice, the second time being a Jacobian actually. So for the second time, for the second time we do this, we basically look at the expression for partial L partial W and then taking its gradient. Actually, the final expression was here. W only appears over here, so then the Jacobian is just going to be the identity matrix. For the cross terms, it's basically a gradient with respect to W and also a partial derivative with respect to B. We observed that when we first take the gradient, the partial derivative with respect to B, the result does not depend on W. So then when we take the gradient with respect to W, that becomes 0. Similarly, the expression for partial L partial W does not depend on B. So when we take the partial derivative of this expression with respect to B, we're going to get 0. So that's where we get the vectors 0 on the off-diagonal blocks. And the last 0 was basically from partial L partial B not depending on B either. So then when we take another partial derivative with respect to B, we get 0. So this shows that L is a convex function in the parameters. So the critical points must be a global minimum. Okay, what we did next was to plug in the value of W. So plug in these conditions into W, and that will basically solve the minimization, the inner minimization problem. And we did it pretty quickly. So the two conditions are in blue and green on the slides. Here, I have replaced all the W's with the blue expression. And next, I just brought in the transpose into the X because that is the only vector. Next, I collected some of these multiplication of sums into double sums. So I've done that for the first term over here. And next, I first split up these summations into 3 separate summations. And then for the middle double summation, I combined them into a single double summation with the summation signs written together like this. And once we do that, we realize that the term in orange and the term in blue are like terms. We have 1/2 of this minus this. That gives us minus 1/2 of that. And finally, looking at the last term and using condition number 2, we got that this last term must be 0. So then, in the end, the final result is the two remaining terms subject to the condition number 2. Back here. Okay, putting everything back. So now we have the inner minimization. Putting that back into the overall dual problem, which did have a maximum in front, we basically had max over lambda of this expression that we just had, subject to the remaining condition number 2, as well as moving this lambda I greater than 0 condition down here. Okay, so it looks like we're out of time. So next time we're going to be looking at Slater's condition and then kind of showing that the SVM problem does satisfy strong duality. So solving the dual problem turns out to be equivalent to solving the primal problem. Okay, so hopefully you guys can take some time to absorb all of this. So I'll see you guys next time. Have a good weekend.